तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were discussing a solution to a set of linear equations. That is what we were doing in the last class. So, we continue with that today. So, we had a system of linear equations of this form, that is a11 x1 plus a12 x2 to a1 n xn equal to b1. So, with n such equations for n unknowns x1, x2, x3 up to xn. What we were discussing was methods for solving such systems of linear equations by way different methods. That is what we were looking at. Okay. So, we saw one method is that we could write this in the form of a matrix, right, and then we could invert this matrix and then multiply it on this side to get the solution. Okay. So, instead of doing that directly finding the inverse of this matrix, we were looking at what the method called Gauss elimination. So, just to remind you that we were looking at this Gauss elimination scheme. We were looking at the Gauss elimination, and then in which we had written the matrix as a11, a12, a1n and a21, a22. We write a matrix of this form. And then our idea was that this, since our set of linear equations can now be written as in this form as I just showed you. Okay. Okay, since we can write the set of linear equations in this form, if we could reduce this, and we also saw that if I multiply any of these rows, okay, by a constant on either side of this equation, that is this equation and this side, if I multiply by a constant, or if I take a linear combination of this, replace one of these rows by a linear combination of two rows, and similar thing here also, and then I will not change the solutions of the equation. And hence we use that method to eliminate all the columns below the first row, and similarly all the columns below the second row here, all elements below the second row in the second column, and all the elements below the third row in the third column, etc., to get a matrix which is non-zero only above the diagonal, and the diagonal and above. So, that was the idea of Gauss elimination scheme. So, for that we replace this one a21 for example by a21 minus a11 a2. So, we divide this whole row by a11 and multiply by a21 and subtract from this. That is what we were doing to get this. So, all elements in this row a2i for example, that is all elements in this row gets replaced by a2i, will go to a2i minus a1i divided by a11 into a21. So, that is what we were doing. Okay. So, if you do this for all the elements in this row gets replaced by this row minus this row multiplied by this factor a21 by a11, and then you can see that when I is 1, that a21 will go to 0 in this case, because this a21 by a11 by a11 that will go to 1, and then a21 by a minus a21 that goes to 0. So I could do for all the rows. Okay. And similarly, I will do a3i as a3i minus a1i divided by a11 into a31, etc. for all the rows, and then I could reduce it into 0. And at the end of this operation, I would have obtained a matrix of this form, which has zeros all below the diagonal. So I will have all zeros below the diagonal elements. So I will have all zeros below the diagonal elements and above non-zero above the diagonal elements, and all these elements would have changed many times. This, for example, this row would change 1 time, and this would have changed n times, etc. n minus 1 time. This would have changed. For each elimination round, all the rows would change. Okay. And then we will get a matrix which is non-zero only above the diagonal element, and hence I can once I have obtained a matrix like that, I can find the solution of this equation, because I can do back substitution. For example, the equation now, the last equation would be a n n x n equal to b n. So this also would have changed in the process. When I do this operations, I also change this side. Okay, so I would get now a n n. I will have an equation like a n n, the new a n n, that is changed n minus 1 times, into x n will be now equal to b n, which will have changed n minus 1 times 2. So from this I can solve this, and I can get x n. And once I got x n here, I can go back, and the next step in the next equation will have 2 values, x n and x n minus 1, and x n I already know x n, so I can compute x n minus 1 from that, etc. Okay. So this is called the back substitution. So to summarize, what we do in the Gauss elimination is to solve a matrix of this form. Okay, if you want to solve a set of equations of this form, okay, we would write these equations in the form of a matrix. Okay, so that the matrix would be given by this. So we'll write it in this form, and actually when you're doing a program, we would actually write it as a 4 by 3 matrix. So the fourth column will be filled by the right hand side of this equation. Okay. So this is convenient because whenever we do an operation on this rows, we also do the operations on this row, so it's convenient to write it in this fashion. And then now we would subtract from this row. Okay, from this row we would subtract this row divided by 3, all elements of this row divided by 3 and multiplied by 0.1. Okay, when we subtract from that, I get 0 here. Okay, and then all elements of this row divided by 0.3 divided by 3 multiplied by 0.3, and subtracted from this, I would get 0 here. Okay, so that's what we would do in the next step. Okay, so that is basically we do this operation AJI goes to AJI minus A1I divided by A11, which is this matrix, this element, into AJ1. So if you do this, okay, all the elements of this matrix this row gets multiplied by AJ1 by A11, and then you subtract from this row and this row. So then you would eliminate the x1 from these two equations, the last two equations. We eliminate x1, and the corresponding matrix would be then given by this. And then we would do this operation for this particular element, then we would eliminate this element, that is, we would eliminate x2 from this equation by multiplying this, by subtracting from this equation divided by 7.033 multiplied by minus 0.1900. So if I subtract from this, then I will get this 0, and that is what the operation I would do next. So I would do that operation now for the second column, okay, and then I would get the equation. The x2 is now gone from this, okay, and the corresponding matrix would be this one. Right. So now I can do the back substitution, because now I know I can solve this equation. X3 is equal to 70.08443 divided by 10. 0.0120. So that is the back substitution which we are going to do, and that will give us x3. So once we have the x3, I can go back into this equation and solve for x2. Okay, so that's what. So we can continue this process. In general, we can write it in this form and then get all the solutions as one by one, x2, and then next is x1, etc. So that's what we have solved. Right. So in the process, what we see is that when we eliminate columns, all the elements in this particular column, we need to multiply this quantity, this row, by a quantity which is A21 by A11, A31 by A11, etc. But they all have denominator A11. So if A11 is very small, okay, or 0, okay, if it is 0, this will not work, this method will not work. If A11, any of the diagonal elements are 0, then this method will not work. Okay. Or if it is very small, then you will have a problem that because the errors in this would be amplified. Okay, because you are dividing by a small number, so the error would get amplified. So that is a problem with this method which we had discussed in the last section. So one way to eliminate such thing is to reorganize my matrix such that so I will reorganize my matrix, okay, such that I will make sure that the diagonal elements are always the large elements. Okay, so that's what's called a pivoting scheme. Okay, so first, what I do is I will find out from this from the column, in this column, I will look at the first column. Okay, so I look at the first column, and then I will see which one is the largest element in that column. So I will just see which one is the largest element in that column, okay, and then I will take that particular row. Let's say in this case A11 was smaller than A21, okay, and A21 was the largest element in the first column, and then I would write this matrix, this row first. So that means this equation, that is A11, A21, A2n into x1, x2, x3, xn equal to B2. That equation goes first. That means I will interchange these rows 1 and 2. So that's the idea. So first I take this column and I find out which is the largest element in that column, and then I would interchange between that and the first row. Okay. So the first row will have the first element as the largest in that column. And then I would go ahead with the elimination scheme, and I would eliminate the rest of the elements in this column. And then I look at the next column, okay, below row 2, okay, row 2 and below, and I will find out which is the largest element in that column. Okay, and then I would again interchange rows in that column, and then I would make this element the largest in that column. So in this way, I would always have the largest element in a particular column as the diagonal element of that particular column and row number. Okay. So that's called pivoting scheme. Okay, so that's what we would do the next thing. So we will use Gauss elimination with pivoting. Okay. So to repeat that, if there is any, so when I have this matrix here, before I eliminate this, okay, even before I do this operation to eliminate the elements in this column, okay, I will first find out which is the largest element in this column is. Okay, and then I would take, let's say this turns out to be the largest element, so that is A1, AN1 was the largest element I had. Then I would interchange these two rows. I would write this equation down and this equation up. That means I will also interchange B1 and Bn. I will do the interchange of that, and then I will go ahead with the scheme and eliminate all of this, all this column, and then I look at the next row, next column, and again find out which is the largest element, and I would interchange that. Okay, so that way I would always make sure that this is the largest number possible in that column. So that way I can reduce the possibility of error. Okay, that's called Gauss elimination with pivoting. Okay, so that's been summarized here. So you go from row 1 to row n, okay, and choose I which is larger than the k, such that aik is the maximum in that row. That means finally you have to find out what is the maximum value, maximum number, which is with modulus. Okay, we are not interested in the sign here. So you got to just find out the modulus and then find the maximum value of that quantity, and then you interchange rows I and k. So for any operation, right? So for any column you will do that. That's I go from 1 to k. Here I said that I keep doing this. So first I do this, and then I go below this, and then in the next element I go below that, etc. And I interchange that, and then I would do the divide by this ajk by akk element, and then I subtract, and I do the, and then subtract and eliminate the columns below. So that's the normal procedure. So this Gauss elimination with pivoting, the only thing which we do is that we would always find out the largest element in a particular column, and then interchange the rows, and you have to keep track of that row interchange if you are also not interchanging B ones. So this is definitely a much more stable and much better way of solving the set of linear equations than a simple Gauss elimination. So now before we go and see the implementation of this in a Gauss algorithm in a program, we would look at some other ways of doing some other ways of solving the set of linear equation. And another method is called LU decomposition, which is also useful for finding the inverse of the matrix. So we will go through this before we actually look at a program. So in this particular case, in the LU decomposition, and such an equation as Ax is equal to B, that is, we have a matrix A and X, so we have a column vector X, right, and that's equal to column vector B. Okay, now this is written as this matrix A, we would write as L matrix L and matrix U times X equal to B. Okay, now this is our column vector x1, x2, xn, and B is the B1, B2 meeting, and this is a lower diagonal matrix, and this is an upper diagonal matrix. Okay, so we will write this as a lower the matrix A as a product of a lower diagonal matrix and an upper diagonal matrix. Okay, and that's called LU decomposition. So that's what we have written here. So Ax equal to B is now being written, the A will be now written as a product of two matrices. L is a lower triangular matrix, lower triangular elements. That means its elements are non-zero only on the diagonal and below. Right. So a lower triangular matrix, which is called L, it has its elements non-zero only along the diagonal and below the diagonal, and you have U, which is the upper triangular matrix, which has only the elements non-zero along the diagonal and above. Okay, that is, we can write this matrices as this form. Okay, so that's an example of L and U. We call this elements as alpha 1 1, alpha 2 1, alpha 2 2, etc., and this is beta 1 1, beta 1 2, beta 2 2, etc. So this idea. So we have now the matrix A will be written as a product of these two matrices. Okay. So our equation now will look like this. So we have L U x equal to B, right? Okay, and then if you we can do it first U x, okay, and then multiply it by L. So now we have a solution, let's say, for the equation of this form, that U x equal to y. Okay, and then we can take that solution y, and then that should satisfy L y equal to B. So we know B, okay, and let's say we know L, that we could write the given matrix A as an L and a U, means product of L and a U, and then I know the right hand side of my matrix equation, that is B, and then I could first solve L y equal to B and get the y, and use that here, and then solve for U x equal to y to get x, because I know U. Okay. So this way the two-step process I would solve. So we would wonder what's the advantage of this. So you see this L y equal to B. Right. So L and U are triangular matrices, as I said. Since L is a triangular matrix, that is L is this one. Okay, it's a lower triangular matrix. So I could write this equation now L y equal to B in this following form. So L y equal to B will be now written as we had L y equal to B. So L is now alpha 1 1 0 0 up to alpha 1 n, and then you had alpha 2 1 alpha 2 2 to alpha, this is 0, and alpha 3 1 alpha 3 2 alpha 3 3 to 0. So we have all the way up to, so last it would be alpha n 1 alpha n 2 up to alpha n n. So we have an equation like this now. Okay. It's a lower triangular matrix. So we had y1 y2 up to yn. Then now that's equal to b1 up to bn. That's matrix equation we have. Okay. So now we can easily solve this, because we can do a forward substitution, that we know the first equation would be this alpha 1 1 y1 equal to b1. Okay, so which I can solve for y1 because I know alpha 1 1, and the next equation would be alpha 2 1 alpha 2 1 b1 plus alpha 2 2 b2 equal to alpha 2 to 1 y1, alpha 2 to y2 equal to b2. So, since I know now y1, I can from this I can get y2 etc. So, I can by forward substitution very easily I can solve for y1, y2, y3, yn etc. So, once I have all the y's, I go back to this next equation, that is Ly equal to b, sorry, now I have y's, I go back to this equation that ux equal to y. Okay. Now, U is an upper diagonal, upper triangular matrix, and we have seen this before, right? In the Gauss elimination, this is exactly what we had. We had the upper triangular matrix, and then the upper triangular matrix, now we can do the back substitution. So, for this equation Bx equal to y, which we just saw in the earlier class. Okay. So, what is the advantage? The advantage is that we do not have to worry about keeping track of the b's here now. Okay. So, we had the matrix A and B, and which we broke into two factors, that is alpha L and U, and Lu equal to A. So, we are still solving A equal to Ax equal to B equation. Okay, we are still solving it in two steps. Okay, so, we do not have to worry about any changes in B. Okay. The only thing is now we have to find out what is L and U, okay, and then we do two back substitutions. So, once you have found out L and U, we do one forward substitution to find out the y's, okay, and then we do one forward substitution to find out the y's, and one back substitution to find out the x value. That is what we will do. So, then now it is left to finding the values of finding the matrix L and U that given a matrix A. So, now that turns out to be not so difficult. So, we are given L and U as A. So, we write L as this matrix, that is alpha 1 1, alpha 2 1, alpha 3 1 etc., and U as this upper diagonal matrix beta 1 1, beta 1 2 etc., and then the U that is equal to A. So, now we can just equate this both sides by just expand this matrix, right. So, matrix equation, and then write n square equations of this form. Okay, so, alpha, so we have two sets of such equations, that will be n square equations, that is alpha IL beta Lj equal to Aij for I less than or equal to j. So, now this is important, so we write them down here again. What we have is two equations, and one is that alpha IL beta Lj sum over L going from 1 to I, that is what we have. Okay. So, L equal to 1 to L equal to I. Okay, so, that will be given by Aij. Okay, this is for I less than or equal to j. Okay. So, that is what the first equation is. Okay, so, the first equation is, so both equations come from this equation, that is, so this row multiplied by this column equal to element A1 Aij element. So, we have the first equation, this is valid for all I going I less than or equal to j. Okay. So, remember, just notice that the limits of this sum is L going from 1 to I, okay, L going to 1 to I, alpha IL beta Lj equal to Aj. This is trivial, you can, when you write down the matrix, you can see that it's trivially follows. The next equation is alpha IL beta Lj equal to Aij, but now the limits are L equal to 1 to L equal to j. Okay. So, that is the next equation. So, the next equation is again alpha IL beta Lj equal to Aij. Okay, now that is for I greater than j, and now the sum is L going from 1 to j, L equal to j. So, L going from 1 to I here, L going from 1 to j here, this is for I greater than j, and this is for I less than or equal to j. Okay, now these are the two equations which we can solve. Okay. So, but we have n square such equations, okay, and we have n square plus n unknowns, okay, because the diagonal elements are non-zero for both alpha and beta matrix. Okay. Since the diagonal elements are non-zero for both alpha and beta matrix, we have n square plus n unknowns, we have n square equations. So, we have to make some choice, so that we choose as the alpha matrix as the diagonal elements to be equal to 1. That is what we do. Okay. So, we will say that alpha matrix, that is the lower triangular matrix, okay, has all its diagonal elements equal to 1. Okay. So, once we have said that, so we already said this as alpha II equal to 1. Okay. So, then we have only n unknowns, and then we can solve this equation. Okay. So, what we do is first we will see this explicitly. We will solve for, we will choose an I, okay, and for all j values which are greater than I, we use this equation, and for all j values less than I, we use this equation. Okay. and then we change the I value and then go again do this. For example, we will do first I equal to 1, and I equal to 1, and then j can go from 1 to n, right. So we will have j going from 1 to n. So we will use this equation. So let us say I equal to 1 and then we have j equal to 1. Okay. So j equal to 1, in that case I is 1, so L goes from 1 to 1. So this is only one element in this here, that is I alpha 1 1 beta L is 1, j is 1 equal to A 1 1. So that tells us that beta 1 1 is just A 1 1. And then we can do j equal to 2. Okay. J equal to 2 we can do in the same I equal to 1, we can do j equal to 2. So now again we will have only one element here because I is only 1. So it is I 1 1 beta L is now 1, j is 2, beta 1 2 is equal to A 1 2. So that tells us that beta 1 2 is equal to A 1 2. Right. By following this, we can easily see that all the we get a general equation here that beta 1 n is just A 1 n because alpha 1 1 is 1. Right. So we can solve that very easily and then get the equation. Okay, now when we choose I equal to 2, then we go to I equal to 2, and then we will see that for I, so for j which is 1, okay, we can't use this equation because I is 2 and j is 1, so this equation does not satisfy because we will use this equation. Okay, so for j equal to 1 we will use this, so we will have only one element L going from 1 to L going to 1, here j is 1, so we will have alpha I is 2, okay, so I is alpha 2 1 beta 1 2 beta 1 1, j is 1, okay, beta 1 1 equal to A 2 1. Okay, that's when we have. Okay, and from this we know what beta 1 1 is, just A 1 1. So I will write alpha 2 1 as A 2 1 by beta 1 1, which is A 1 1. Okay. So notice this, that is alpha 2. So now we have got alpha 2 1 and beta 1 1, beta 1 2, or all the way to beta 1 n. So then now next thing would be j equal to 2, right? So j equal to 2 we have to use. So when you do j equal to 2, again we go back here, okay, and then we write this equation. Now I is 2 and j is 2, so L goes from 1 to 2, so there are two factors in this sum. So we will have alpha 2 1 beta 1 j is 2, so beta 1 2 plus we will have one, I will write it. So we have now I equal to 2 and j equal to 2. So when we do that, okay, we are going to use this. So we have two parts in that sum, that is alpha 2 1 beta 2 2, okay, j equal to 2. So beta 2 2 beta 1 2 is plus, and then we will have alpha 2 2 beta 2 2 equal to A 2 2. So that's what we have. Okay. So we already know what is alpha 2 1 is, we have found out that here, and we know what is beta 1 2 is, that we found out from here. Okay, and if we go everything, we can just get the beta 2 2 from this, and then we will write beta 2 2 as A 2 2 minus alpha 2 1 is A 2 1 minus A 2 A 1 1. So that is A 2 1 minus divided by A 1 1 into beta 1 2 was A 1 2. So that is okay. So alpha 2 2 is 1. So that is so we can continue in this fashion. So okay, then I can do for all j equal to 2 3 etc. So you will find that in general I can solve for all of this, and I can get beta 2 I, okay, for all elements in there, for all j values higher than 2, okay, for all j values higher than 2 I can use this equation, and then I would get an equation of this form, that is I will get that as A 2j minus A 2 1 A 2 1 divided by A 1 1 into A 2 A j 2. I would get, so I would have to do use, so I will write the next element beta, all the general element beta 2j as a 2j, that is what I would get here, because I is 2 and j is any j value. So a 2j minus, I will have in general the solution as a21 divided by a11 into a1j, that is what I will have. Okay, so that will be the general solution, which you can easily check. Okay. So now why I wanted to do this here was because of the following reason. So I do this elimination by this two-step process. Okay, I have two equations. Okay, and I am getting the alpha and beta elements by for picking up I and then doing for all I greater than j this equation and I less than j this equation. I am using this. Okay, and in that way I can actually solve by going back and forth. I can solve for all alphas and all betas provided alpha I is equal to 1. Now that is important. Okay. So now having done this, okay, now you will notice that the elements which you are getting, okay, that is we find that the first row of the beta, okay, is just simply the same as the matrix itself. Okay, the first row of the beta is the same as the matrix itself, a1 beta 1 n is a a1 n. So now we are writing the matrix in this form. If you remember that we had the matrix as alpha 1 1 0 0 0 0 and alpha 2 1 alpha 2 2 0 0 etc. Okay, so we had that matrix and then we had beta 1 1 beta 1 2 up to beta 1 n and then beta 2 2 beta 2 n and these elements were 0. Okay, so the last what beta n n. That was our A matrix. Okay, that's what A was. So now we find the A21 here. So we know the diagonal elements are 1 here. Okay, that's what we are chosen to be. Right? And we find the alpha 21 is A21 by A11. Okay, so it is similarly A21 by A11, and in general the beta, the next element beta here. Okay, so the beta 22 is A22, which is the A element here, minus this A elements in this row, okay, divided by A multiplied by A21 by A11. Okay, that is what we are getting here, the new element here. So the A beta 22 is A22 minus A12 multiplied by A21 by A11. So now that is exactly what we did when we did the elimination, okay, the Gauss elimination. Right. So it turns out, so what we are actually getting, this beta matrix which we get here, okay, is exactly the same as the matrix which you would get on Gauss elimination. Okay, simple Gauss elimination, what we get as a beta as a matrix at finally the upper triangular matrix, that matrix is the same as this beta matrix. Okay, so that is the same as this beta matrix, and the factors which we use to eliminate, right, to do the Gauss elimination, okay, that is we were taking the first row and we were taking in the second row was subtracted from the second row we were subtracting the first row multiplied by a factor, okay, and that factor is A21 by A11. To eliminate the columns below the matrix A, below the first row, all the elements in the first column below the first row, we multiply the first row by a factor which is A21 by A11, okay, and similarly and the next one by A21 by A11. So the whole row was multiplied by A21 by A11, and that is exactly what goes in as alpha 21 here. Okay. And similarly we can show that what goes as alpha 22 as alpha 22 is what goes as alpha 31 here. Okay, the next element alpha 31 here is the factor which you have to multiply the first row in the Gauss elimination to get rid of the elements in this column, in this row here, okay, on the first column. So what in summary what I am trying to say is that these operations which we do here, okay, to get this beta and the alpha matrix, okay, finally produces this operations finally produces a matrix beta which is the same as the upper triangular matrix which we got from the Gauss elimination scheme. Okay. Upper triangular matrix in the Gauss elimination scheme now goes as the beta matrix here, that is the U matrix here. Okay. and the factors which we use to eliminate those column elements below the first and second row, and all the elements in the nth column below the nth row, okay, was that factor which we used to multiply that was given is the element alpha ij. That's what we would find. Okay, that's what we find from this simple scheme. Okay, so that means that by just using the Gauss elimination itself, we could get both the alpha and the beta elements, or the L and U matrix we can actually get from the Gauss elimination. Okay, and then we can actually see this in a small calculation just now. Okay, I will show you that. So the only difference is that in the Gauss elimination, remember, we actually whenever we transform the matrix A, we also transformed this B. Okay, so we did that, okay, in the Gauss elimination scheme. Okay, but in this case here we don't have to do that, because what we do is we just simply store these factors in the alpha matrix. Okay, that's what we are doing. Okay, we simply store these factors ALI by ALL in our alpha matrix. Okay, this is the ijth element of the alpha matrix. We will just store this in the alpha matrix, and then we will do a two-step elimination, a two-step process, one forward substitution and one backward substitution to get. Okay, so these are the factors which are stored in the alpha JL element of the lower triangular matrix. Okay, so we will see this in a small. We can use a small example to see this. Okay, we will try to solve an equation of this form. So let's say we have an equation of this form, which we saw yesterday as an example. That is 1.1 and 6, 2, 1, 1, 4, 2. So we want to solve an equation of this form, x1, x2, x3 equal to 7.65. Okay, so let's say we have an equation of this form to solve. Okay, so what we do, as I said, we eliminate these two elements, okay, and then this element, and we would get a upper triangular matrix. So that's what we will be doing. Right? So we will do that by first we will multiply this row by 2, right, all these elements by 2, and subtract from this. Okay, so that will go to 0. So then multiply this by 2. So 2 into this row minus this. Okay, 2 into this row is subtracted from this row, that will go to 0. Okay, so that we will get that as 3. Now the new matrix would be 3, 2, 1.1, 0. So when I multiply this by 2, I will get a minus 1 here, and I will get a minus 1.2 here. And then I would multiply this row by 1 by 3 and subtract from this to get 0 here. So that is 1 by 3 is my factor. Okay, so the factor here was 2, remember, to get this, and the factor here is 1 by 3. Okay, so when I multiply by 1 by 3, then I would get 0, 10 by 3, 4.9 by 3 as the factor. Okay, so that's the factors I would get. Okay, now I had 1 by 3 factor here, and I had factor 2 there. Okay, and then I can now further reduce this, right, by multiplying this row by 10 by 3 and adding to this. Okay, then this will go to 0. So this will get added by multiplied by 10 by 3, okay, and added to this. Okay, so this will change, will become this multiplied by 10 by 3 added to this, and this will go to 0. Okay, so that factor is a minus 10 by 3. Okay, so with a factor minus 10 by 3 going here, I would get this as 3, 2, 1.1, 0, minus 1, minus 1.2, 0, 0, and then this turns out to be just minus 1.1 by 3. Okay, so I got now a upper triangular matrix. So what my claim is that this is my beta matrix. Okay, so my beta matrix is exactly the same as this. Okay, so what is my alpha matrix now? Alpha matrix has all the diagonal elements as 1. Okay, and alpha 2, 1, this one would be just 2. Okay, and alpha 3, 1 will be this 1 by 3, and alpha 3, 2 would be minus 10 by 3. Okay, so that's a claim. So my beta matrix is, so my alpha matrix now is 1 0 0, and then I have 2 1 0, and then I have 1 by 3 minus 10 by 3 1. Okay, that's my alpha matrix now. Okay, that's these three factors I put in there. Okay, and my beta matrix is now 3 2 1.1 and 0 minus 1 minus 1.2 and 0 0 minus 1.1 by 3. Okay, that's my beta matrix. Okay, now you can see very simply that if you multiply these two, you will get this matrix A back. Okay, so I have actually done a decomposition of this matrix into a upper triangular and a lower triangular matrix by doing this. Okay, that you can very easily see that. Okay, so now you could actually solve this. Now we have not done anything to the B equation at all. We just left it as it is. Okay. So my equation now is that this into x1, x2, x3 is equal to 7.65, 13.5 and 16. Okay, that's my equation. So now what I'm going to do is to do again a two-step process. Okay, I'm going to say that I have an Ly equal to B. So this was a set of equations which we had, right? Lux equal to B, and then we wrote ux L in the ux equal to B. That means we have now two equations, that ux equal to y, okay, and then we have Ly equal to B. Okay, so that's what we are doing. So first we do Ly equal to B and solve for y, and then we substitute that here and get the ux. Okay, so that's what we are going to do. Okay, so we will use this equation Ly equal to B. So we know L. Okay, so we have 1 0 0 2 1 0 1 by 3 minus 10 by 3 1 into some y1 y2 y3 that's equal to 7.65 13.5 16.0. okay, so we can solve this this equation. Okay, and when you solve this equation, you would find that y1 y2 y3, so we'll get y1 as, so you can do this by forward substitution, as I said. So the y1 will turn out to be 7.65 straight away, right? Okay, and then you can find y2 will be equal to minus 1.8, and we get y3 as 10.45. Okay, so it's a forward substitution. So we'll get y1 straight away, and then you have 2y1 plus y2 as 13.5, and I know y1, so I can compute y2 from that, and then I have 1 by 3 y1 minus 10 by 3 y2 plus y3 as 16, so I can get y3 from that. So this will lead to that solution there. So once you have y1 y2 y3, okay, and now I can use the equation that ux is equal to y. Okay, so now we are going to say this ux is y. That's what we put in here, right? So now I can use ux equal to y. So I'll do that. Okay, so my u matrix being 3 2 1.1 and 0 minus 1 1.2 and 0 0 minus 1.1 by 3. Okay, so and then I have that x1 x2 x3, which is the solution which I want to find, and the right hand side would be now 7.65 minus 1.8 and 10.45. Okay, that's what you would have. Now we have to do back substitution here. So we have to do first x3, so minus 1.1 by 3 x3 equal to 10.45. So we can solve that, and then you would get x3 as minus 28.5. Okay, by just doing this x 1.1 x by 3 x3 equal to 10.45, and then I have this equation that minus x2 plus 1.2 x3 is equal to minus 1.8. That I know x3 here, I can substitute that here, and then that would give me x2 as x2 is equal to 1. Okay, that's what we would get, and then I can write in the last equation, that is 3 x1 plus 2 x2 plus 1.1 x3 is equal to 7.65. So from that I can get x1, and that turns out to be, sorry, x2 turns out to be 18 and x1 turns out to be 1. Okay, so you can do this calculation and then you would get this solution. So what have we done so far? So we have done this A matrix as L times U times X, okay, and then LUX equal to B. So we took UX as some Y, okay, and we solve for Ly equal to B, okay, and we got Y from here, okay, and then we put that back into this equation, then it says UX. So now we solve for this and got Y, okay, and then we said that UX is Y, so UX equal to Y is here, and then I solve for X. So that's a general method, and this can be programmed, okay, and it can be written as a simple algorithm to solve this. So what the advantage is, so we don't have to do anything to the B values, okay, we don't transform the B values, and also notice that we don't need any extra space to store L and U, because you had one matrix A, right. Now that matrix A is been now split into two different matrices L and U, and we have chosen the diagonal elements of L to be 1, and so that we know that, so there is no need to store that, and we are not going to use that, right, because we know that it is 1. Okay. So in the equations which you use later, we already assume that this is 1. Okay. So we don't need to store the diagonal elements. So the diagonal elements and above of the A matrix can be used to store B, this U. Okay. So diagonal elements and above of the original A matrix can be used to store the U matrix, that is the upper triangular matrix. Okay. So that is so when I write this in the A equation, okay, the A matrix, okay, so this part of my U matrix can be simply stored in the A matrix itself, okay, and the elements below the diagonal of the A matrix can be used to store the L matrix. Okay. So we don't need any other storage apart from the original A matrix itself. Okay. So if you are dealing with large matrices, this definitely is very helpful, because storing two-dimensional arrays is always a big problem on a computer. Okay. So here is this particular LU decomposition method will actually help us solve that problem. Okay. And then we can and also that the forward and backward substitution is extremely easy to program. Okay. So that's what we would see in a program after this. So here is a program which implements the LU decomposition of a matrix and then find a solution, use that to find the solution of a linear equation. Okay. So here is this program. So we have the matrix D, which would be which is our matrix to be decomposed. Okay. And this little d column vector is the solution, is the right hand side of the linear equation, and we will get the solution in this column vector S. And now the intermediate value, remember we had this y is equal to d, that the solution of that. Okay. So we write the matrix D as now L into U. So L into U into X equal to D is our equation, right. So from that, so L into U into D, L into U into X is equal to L in U into S here, not X, S equal to D is our linear equation. So now that U into S is what we write as Y, and then we solve Ly equal to D first. So Ly equal to D is solved first, and then we will use that Y, and then you say U into S is equal to Y as the next equation and solve for Y. So these are the two, this is actual solution S, and this is the intermediate value which you would get from the equation L into S is equal to L into Y equal to D. That solution we will get from in Y. So here is the matrix D, okay, so which is the initial matrix which you are given. Now we want to, and then the solutions are on the right hand side of the equations are here in the D0, 1, 2, okay, and then we will have we will print that out here, and then we just see the matrix first, the matrix equation. So I'll just show you. So that's a full matrix. Okay, so you have the matrix elements as 3 2 1.1 6 2 1 and 1 4 2, and the right hand side of the equation is 7.65 13.5 16. Okay, so these are linear equations of the form 3x1 plus 2x2 plus 1.1x3 is equal to 7.65, etc. So that's a full matrix, and then we have this code here. This would now help us put the split the matrix into L and U. Okay, so remember, we are using the method here. The method we are using here is the elimination process. So we use the elimination, the Gauss elimination method to get the L and U matrices. That's what we are going to do. Okay. So first we take k equal to 0, that's the first row, okay, and then we'll go from j equal to 1 to n, that is all the rows below that, right, all the rows below that, and the first column, and we will eliminate all the first column of all the rows. That's what we're going to do first, right? Okay, so when you do that, all the columns get affected when all of them change, but the factor which we need to multiply the first row to eliminate all the rows in the first column is this one, that is d j is 1, d1 into k is 0, so d1 0 by d0 0, that's the first element, that's the factor which we use, right, that factor is written as x here, and that is subtracted from all the elements in that row, okay, for all the rows, and then same for all the rows, we will do that this way. Okay, when the rows change, this factor will change. So for one row, one factor, right? So one row, the whole row is multiplied by one factor, okay, which is x, that is given a row j, which is everything below k. Okay, the factor is djk divided by dkk. So that's the same for all the elements in one row. Okay. So now that factor in the LU decomposition we discuss, that factor goes as the element in that column, right? So as I said, for every row in one column, right, for every row we have the same factor, right, for every row we have the same factor. So when you take the k equal to 0, that is the first column, okay, then we eliminate every elements below that first row, okay, using different factors for different row, right. So that is what this factor here is, the djk by dkk is. So I take a row j, okay, and I have a factor, and that factor is now stored in the djk element, because djk element is going to go to 0, right. And then I take another j, okay, and I get a new new factor djk by dkk, that goes into this. Now that's the second, I take the first row, I get d1k by dkk, that is d1 0 by d0 0, that goes as the d1 element, d10 element, which is now actually eliminated. So I store that factor there, that is the element of my L matrix, right. So L matrix is composed of these factors which we use to eliminate columns. Okay, so that has been stored there. Okay, and then I take the next column for the next row, that is j I change, right. So then I have a new factor, okay, and that is d2 0 by d0 0, and then d2 0 is stored in that factor x is stored in d2 0. So at the end of this process, I will have the one round for k equal to 0 if I did. The first column is now, first column below the first row is all 0, okay, that's what I showed here. Okay, it's all the first column below there should be all, these are all gone to 0. But what I do here is I store that element which I have to multiply, okay, in that column. Okay, so now that's what I have shown here. Okay, so now you look at this. I had to multiply this row by 2 and subtract from the second row, first row by 2 and subtract it from the second row. Okay, first row by 2 and subtract from the second row to make the second row 0. So that factor 2 I have actually stored in that element. This is anyway 0, so I stored that there itself. So this is part of my L matrix. Okay, this is part of my U matrix, and this is part of the L matrix. Similarly, I had to multiply the first row by 1 by 3 and subtract from here from the third row to make the third row first column 0, and that this 1 by 3 is stored there. Okay, so it's stored here. So this is again part of my L matrix. Okay. So, similarly I will do now for the second column. Okay. This now all now the second column also I will do the same thing, and then after I finish all that, okay, I have the second column done. Now the second column, to make this second column last element 0, okay, I had to multiply this one by again I have to divide this by 0.33 and multiply it by 2. So, that factor has been stored here. Okay. So, this is now by this time I have completely decomposed the matrix. So, now the first row and so now I have the L and U matrix both put in this. Okay. So, the U matrix is given by this whole elements 1, 2, 3, right, and the L matrix is given by this 1, 2 and 3 elements. Okay. Or everything else is U matrix. Okay. The diagonal elements of the L matrix is, we know, is 1. So, we do not need to store that. So, this 3 are these 3 are the elements of the U matrix. Okay. Then you can see that I did not change the right hand side because I do not need to change the right hand side. Okay. And then I do the forward substitution to get the Y matrix, that is this one given here. The Y matrix is obtained by forward substitution. So, the first element does not change, as you can see from here, this does not change here, and the other two change, and then I do the backward substitution to get the solution, that is the x. Okay. So, that this is a solution of the U x is equal to y, and this is a solution of L y equal to d. Okay. So, I got y here, and then I substitute a U x equal to y, and I got a solution here, and this is I am just comparing that when I substitute the solutions back into my equation, do I get the right hand side correct? Yes, I get almost correct. There are round off errors you can see here. Okay, that is what we will see. So, I have not shown any pivoting techniques in this. Okay, so I will show the pivoting techniques in implemented in a program in the next lecture.